in dimension 8. Thank you very much.
Yeah, so thank you. So maybe one thing I wanted to say is that maybe this is not a talk, this is rather an announcement. So I'm only starting my journey in formalizing things, and maybe I'm not ready to give a whole talk. But instead, maybe what I can do, I'd like to speak about project I've just started. And the goal maybe is not so much to tell you about the progress we have done, rather than to ask for help and maybe to encourage people to join the project. And so the idea is very simple, is that I would like to formalize my proof of the my solution of the sphere packing problem in dimension 8. And somehow the probably, as you know, that there is somehow a long historical bond between solving sphere packing problems and formal mathematics established by Tom Hales. And so I thought that maybe it would be somehow, and I got very curious about math for formalization, but it's still a long time for me to learn how it works. So I thought maybe why not making this project, and maybe this will be my introduction to the subject. And so, okay, so here's the theorem I would like to formalize. So the theorem says that no packing of unit balls in the Euclidean space has density greater than that of the E8 lattice packing. And so now we have a proof. So now that we know the sphere packing problem, it has been solved in dimensions 1, 2, 3. So 1 is somehow trivial, 2 is rather simple, 3 it's the famous Kepler's conjecture, which is also now a theorem of Thomas Hales and his collaborators. And so the solution of the problem in dimension 3 was long and technical and included a lot of computation. So this formalization was needed to have sufficient confidence in the proof. And so now we also know how to solve this problem in dimensions 8 and 24. And in dimensions 8 and 24, it seems to be that these are very special dimensions. So 3, it seems that 3 is a somehow mean dimension where ugly and unpleasant things happen, and the problem is solved only because 3 is a rather small number, while 8 and 24 are actually big numbers, big dimensions. However, they are very special, and very special structures exist there. For example, the E8 lattice and the Leech lattice, they are extraordinary mathematical objects, and that's why probably it's not difficult to prove that they are optimal. And so the solution in dimension 8 and 24, it's quite different. It relies on Fourier analysis a lot, and certain what is called the theory of modular forms, so for functions with very special symmetries. And so the proof of the sphere packing problem in dimension 8 and 24, it relies on a method called linear programming and the theorem of Conan-Elkis, which was proved in 2023. And here it's an interesting example. It's a proof by providing a certificate. So what theorem of Conan-Elkis says us is that if we can construct a function, a Schwarz function, and this Schwarz function satisfies certain, okay, so I think here there is a typo in my slides, so something disappeared here. So, okay, so here the condition should be that the function itself should satisfy an inequality, and also its Fourier transform to satisfy an inequality. And while I was preparing a file, somehow the head of a Fourier transform disappeared, so I apologize for that. The first condition is for the function f, and the second condition here is for its Fourier transform. And again, so here also there is a typo. So here it should be the value of f at not at x, but at 0 divided by the the value of Fourier transform at 0. So if you can satisfy compute the Schwarz function and the Schwarz function itself and its Fourier transform satisfy some inequalities, then we get a bound on the density of a d-dimensional sphere packing. And so what is yes, so then the way to solve a problem in dimensions 8 to 24 is just to compute this function which satisfies the best possible inequalities. So where this number is as small as possible. And we already know that in many dimensions, we cannot find such a function which would completely solve the sphere packing problem. For example, we know that in dimension 3, this method would not give optimal result. It will not give a complete solution, and this is a result by the recent result by Rupert Lee. But in dimensions 8 and 24, actually we are lucky, and this method of Kohn and Elkis, which is just a reduction of the sphere packing problem, it actually works perfectly and gives the perfect solution. And so so for some reason on this case here, I think it's maybe it's not my mistake, maybe it's a mistake of the computer is making. Somehow it did not like my Fourier transform signs. So here again, so we prove that there exists my main somehow ingredient of the proof is the proof of the existence of a Schwarz function, which satisfies this inequality. So the function itself is non-positive for when the distance from point to origin is bigger or equal than square root of 2, and the Fourier transform, and here the Fourier transform sign is missing, unfortunately. So the Fourier transform is bigger or equal than 0 for all points the 8-dimensional Euclidean space, and our function is normalized in such a way that the value of function is 0 and the value of its Fourier transform at 0 equals to 1. And so this is somehow my suggestion is to formalize the proof of this theorem. And the paper where this theorem is proven, it's only 16 pages long, so I hope it should not be all that difficult, but of course there are some caveats in here. So here is a plan of the proof, somehow main elements of the proof, and the proof itself, so I somehow here of course all mathematical papers, they are organized in linear order, and so here if you go somehow vertically and then from left to right, you will see how the dependencies in the proof looks like. So first, if you want to formalize this, of course, we need to, and then the paper, it's almost implicit in the 16 pages, is that we need to have certain number of facts, basic facts about sphere packings. And then we also need to know some basic facts from Fourier analysis. And as I already told you, the proof itself, it relies on linear programming, in particular on the theorem of Kohn and Elkis. And then starting from here is actually maybe from here is the content of my paper, and there some still we are if you want everything to work, we need to know some basic facts about complex analysis, in particular about counter-integration of holomorphic and meromorphic functions, and also some basic facts on modular forms. And after we have developed all these basics, we should be able to construct this function g, which we the definition which was suggested by Stephen Miller to call this function a magic function which magically satisfies the conditions of optimal sharp conditions in the Kohn-Elkis theorem, and therefore magically solves the sphere packing problem. And so would have to formalize the construction and of this magic function and prove its properties. And then there is a last piece where we need to prove also certain inequalities satisfied by this function, which essentially are reduced to proving certain inequalities for certain very explicit modular forms. And when all of this is done, then we have the main theorem. Then we know that the sphere packing constant in dimension 8 is exactly this number, which is the density of the E8 lattice packing. And so a few months ago, Kevin Buzzard visited the PFL and he somehow encouraged me to start this project. And luckily enough, there is a master's student from UCL London who's now visiting at the PFL. So his name is Sitar, and together with Sitar, we started working on formalization. And because I never worked on it before, so for me it was a rather steep learning curve. So I had to learn a lot, and so the main somehow things we were wrestling with were some technical difficulties for now, but I hope that now maybe we can go up to speed and actually go into mathematics. And so what we have done so far, we have decided to go the usual way. And as I see from other examples of recently formalized theorems, is that the usual way is to create what is called the blueprint of the project, and yeah, to split the whole proof into digestible definitions, lemmas, and theorems, and then step by step formalize it. And the blueprint, it's essentially a website where the human readable mathematics, the mathematics in essentially a mathematical paper, is linked to the Lean code, and there's also a dependency graph which helps to track progress and see which statements have already been formalized, which statements are not properly formalized, to see how different elements of the proof depend on each other. And so here, what I've somehow the auto-generated dependency tree we have some right now, it's incomplete and also looks a little ugly. And so here I've created somehow a simplified version of that. So here, of course, are not all the theorems and not all the definitions, but I tried to somehow identify the main of them. So this is more or less, I would say, main elements of the proof, main statements that need to be proven. And as we are on this somehow at the beginning of the journey, so probably some important things are still missing here, and maybe certain things inside of the proof have to be broken into more steps. And I think now what is more important is that there might be some facts from, for example, here we did not even start thinking about what we will need to formalize in complex analysis to make everything work. And yes, and so this is more or less somehow here, right? It's a blueprint of a blueprint, and so I apologize, something did not render perfectly on this slide. So. And so these are more or less the dependencies that we have. So there is this basics on sphere packings and some important facts from Fourier analysis, but still rather basic. And then the proof of Kohn-Elki's theorem, it of course depends on this knowledge on the sphere packings, on main definitions and main facts about them. It also depends on Fourier analysis, in particular, it depends on the Poisson summation formula, which we are, as our first exercise, we are trying to formalize the somehow more the Poisson summation formula and more general version of it that is already present in Lean. Then we would need certain facts about modular forms, and as I see that Lean already has a library about modular forms, but then we would have to check whether all of the facts that we need, they are already present there, and they usually some very explicit facts about computing, for example, computing Fourier expansion of particular modular forms, or proving various representations for Fourier coefficients of modular forms, and proving estimates and asymptotic estimates for coefficients of, or maybe not so much estimate, like actually effective estimates for the Fourier coefficients of modular forms. And then there is a part which probably is somehow most very explicitly written in the paper, which is the construction of magic function, constructions of different several different integral representations of this function, and proving certain facts about it, for example, computing some of its special values of the magic function and its Fourier transform. And then finally, final step would be somehow this maybe a bit of a dirty part, which is we have to prove these explicit inequalities for modular forms. And here there are different somehow, actually the first version of this theorem was proven in 2016. And since then there have been some improvements. So maybe these inequalities, maybe there are actually better ways of formalizing them than just following my original work. For example, when we proved the sphere packing problem in dimension 24, there I think we did a much more robust procedure, which should be much more suitable for formalization. Also, rather recent development, there is a paper of Dan Romik, a mathematician who actually proved all these inequalities in so to say, without referring to lengthy computations, just by doing somehow human readable, human verifiable estimates of modular forms. So maybe it's also a nice way to formalize the proof of the inequalities. And so finally, after inequalities is proven, then we know that our magic function indeed satisfies all the necessary inequalities of Kohn-Elkes linear programming theorem. And then the existence of magic function combined with Kohn-Elkes theorem gives the solution of the gives the complete solution. And so maybe so here are a few things I would also like to hear. There are a few people I would like to thank so far. So first, I would like to thank Sidhar, a master student from UCL, who helped from Imperial College in London, who helped me with all in this project so far, who was extremely patient with me. I would like to prove Kevin, who always answered all the questions and who actually encouraged me to start working on this. Also, I would like to meet two people whom I never met personally, but with whom we interacted directly or indirectly. So with Patrick Massoa, he's a mathematician who developed the software for making blueprints, and it seems that once a mathematician manages to set it up, then it makes this very nice environment easy to work. And I also would like to another person called Utensil, who is somehow a lead wizard, who helped us with many technical problems when myself and Sid were not able to solve them. So Utensil helped us a lot. And so here are the links for the project so far. So at the moment, everything is in a development stage. So we have created a blueprint, and blueprinted essentially it starts. It is my paper from 2016 with changed a little bit to be more lean friendly. With somehow maybe I started splitting it into more definitions and more lemmas, so that it would be easier to formalize them. Also, of course, we're adding more preliminary results or results of other papers, which also need to be formalized for all project to work. And yeah, so if you are, I think the repository is not public at the moment because we are still working on it, and maybe we have to somehow, if you want to admit more people working on the project, we would have to come up with some good system, for example, how to so that everything stays intact and there is no contradictions, and somehow how to harmonize different efforts. But then I think they believe that blueprint should be visible from anyone should have access to it. And yeah, so it's still in a construction phase, so not everything looks perfect there. And yeah, here are different, it's possible also to check our currently existing dependency graph, but it's also it's not complete yet, so we are still working on that. And so probably that's all what I wanted to tell you about, and now I'm happy to answer your questions.
Thank you very much.
Maybe I have a small question. So is there a